morning, everyone. I am Allessandro Negro, and I'm the GraphAware chief scientist. Let me say that I'm so glad to be here today to speak at this amazing conference. So, does anybody remember this? Okay, not so many. So these all started in the early 1980s. At the time, without internet and social media, this was definitely an interesting and ingenious solution of putting missing children's face in front of millions of Americans all over the country. But unfortunately, it had a few important limitations, because it could be, unfortunately, too late, and the missing child had to be visible in public. Of course, nowadays, we don't need milk cartons anymore, because we have Amber Alert, social media, instant notification. So the distribution challenge has been solved, but other more important challenges have emerged. Because nowadays, detectives are facing a paradox. On one side, they have access to more data than ever before. Yet connecting the dots between these seemingly unrelated data within this sparse information has become increasingly complex and time-consuming. And time is against them, because the first 24 to 48 hours are crucial to increase the chances of finding the missing child alive. So investigators must process an enormous amount of structured and unstructured data and also mix them with physical evidence. And they have then to identify which pieces matter the most, connecting these seemingly unrelated data, and try to create a coherent narrative revealing who, when, why, and in particular, where the missing child might be now. This is definitely an immense task while the clock is ticking. The missing child case is just an example, of course, and the investigative process I just described is not unique in the law enforcement domain. Because across many domains, different professionals are facing similar challenges. They all have to access and navigate an enormous amount of data, some specific, some generic, distributed and scattered across a variety of data sources. They have also to apply a specialized domain experience and make critical decisions, sometimes under time pressure, as we said, or because it is vital for people. And they also have to consider specific details for each case. For example, in the healthcare case, physicians diagnosing complex conditions must consider patients' medical history or test results, symptoms, trying to, and they have to match this with generic practice and latest research. Exactly like detectives, they search for patterns and connections, and they have to formulate hypotheses, verify them, and they have to follow a path. Maybe wrong, and then they come back and start from scratch. And the same applies to other domains like financial for detection, legal discovery, supply chain optimization, you name it. So at this point, you might be wondering why I'm giving you all these examples from multiple domains. Well, I'm sure, because I did as well, that you heard a lot of interesting applications of generative AI in this conference. And indeed, the new AI technologies are definitely offering remarkable capabilities, and many of these are very useful even in the domain that we just mentioned. And I listed here a few of them. That's all impressive. But the question I have is, can these technologies truly support the investigative-like process that we just described? For example, how can they help detectives to find missing children before it's too late? Or how can they assist physicians in diagnosing complex conditions accurately? Well, the milk carton example taught us an important lesson that we should remember, that a solution can be innovative and widely adopted, but still not addressing the core challenges. In our case, we don't need only information retrieval. We need technologies that can support the complex and contextual reasoning that this type of task will require. And unfortunately, generative AI struggles when applied to these specific type of tasks. And I'm not speaking about technical shortcoming. We are talking about real barriers that make these technologies to struggle when lives depend on it. And among the others, of course, you can imagine how for example, the black box effect or nature can't provide the chain of evidence required in legal proceedings or as a justification in medical diagnosis or medical treatments. And I'd like to, and the same is for hallucinations, of course. These could mislead investigations and diagnosis. And I'd like to clarify that I'm not against or I don't want to mind the value of generative AI. What I'm saying is that with these specific use cases or in these conditions, these limitations require generative AI to be paired with other technologies, in particular with something that could represent the contextual knowledge that we need for this specific type of application. So the right question is, what format should we use for representing this knowledge properly to, let's say, complement, support, and leverage the generative AI tools' power? And of course, the answer, as you can guess from the title of this presentation, is the knowledge graph. By using this data model paradigm, we can create an ideal unified repository, a single source of truth or a single source of intelligence where all the structured data sources can be transformed into a consistent graph format, regardless the schema or the access pattern of the original data sources, where it's easy to store, for example, entities and relationships automatically recognized by generative AI tools from unstructured data like text, images, videos, etc. When we can store via spatial or geographical or geo or temporal relationships, not only what happened, but also when and where, which is fundamental in some investigative case. And of course, by using weighted connections, we can represent let's say, the trust of some of the data sources that we ingested. So the flexibility of the data model is what makes knowledge graphs, and we have seen these many times in this conference, the perfect companion for generative AI tools, in particular in the context of critical decision-making processes that we are addressing here. By using a knowledge graph, actually as a unified information access, we bring two major advantages. From the human perspective, this literally eliminates the need from detectives or physicians, for example, to search across multiple data sources, cross-referencing data, connecting the dots, because this will come for free with the knowledge graph. And from a machine learning perspectives, knowledge graphs empower generative AI tools so that they can process a larger amount of data more effectively because the knowledge has been already, let's say, distilled and organized in a machine-readable format. So with the knowledge graphs, generative AI, and in particular, as we will see, large language models, can provide a more accurate answer. They can limit hallucination, and they provide this verifiable fact provenance, which solves one of the issues that we mentioned before, the black box effect, but not only. Because by using these two powerful technologies in combination, we can set the foundation to create an intelligent advisor system. That the purpose of this AI-based tool is to support humans, specifically in critical decision-making processes. And in our ideal scenario, we would like to use the strengths of both these technologies, because knowledge graphs can provide these well-organized source of information where we can store real-world entities and concepts in a natural way, together with their relationships. And this can be done for generic knowledge as well as for contextual and specific knowledge. On the other side, LLMs can provide this sophisticated natural language understanding that can be used during the knowledge graph creation or during the query of the graph, or by extracting a lot of data from the graph, a lot of insights. We can use LLM to create a human-readable, human-friendly output as reports, for example. But let me show you how this will work in practice with a concrete example. Since we started our journey with this missing children case, I would like to continue with that, even because at GraphAware we are quite specialized in law enforcement. But remember that what I'm giving you as an example will work in any of the domains that we discussed before, and not only. We will consider this J.C. Dugard case. I don't know if any of you can remember it, but this is particularly of interest for two main reasons. First of all, she was found alive, which is, of course, good for her, but also good for us because we've got a lot of insights from this abduction. And this case specifically reveals a serious issues or failures in the investigative process, because it took 18 years to find her. It was a long period. So let's walk through what happened in reality, and then we will do the exercise of imaging a different outcome based on the use of this intelligent advisor system. So everything started in California on June the 10th, 1991. J.C. was, at the time, was just 11 years old, was walking to her bus stop when a gray car suddenly stopped by and someone pulled her in the car. Her stepfather assisted, witnessed the event, but he can't do that much. The kidnappers were Philip Garrido, a known sex offender with a long history of rape and kidnapping, and his wife. They took J.C. to their home in Antioch, California, 170 miles away from the abduction site. What is really shocking about this story is that there were many missing opportunities to rescue her. Because during these 18 years, actually, parole officers or police officers visited Garrido's home more than 60 times, and all the signs were there. Because neighbors reported many times strange children behavior in the backyard of their property. And in 2006, imagine that someone called the 911 reporting specifically children living in tents in the backyard of their house. But despite of this precise tip, police officers weren't able to find J.C. In reality, J.C. rescue came from Garrido's mistake rather than police officers connecting the dots. Because Garrido tried to bring J.C. to UC Berkeley campus, trying to get the permission for a religious event. And the campus police officers noticed something strange, so they called him with her, that he introduced as Alyssa. And finally, when she was questioned alone, she revealed her, let's say, real identity, and she was finally rescued and free after 18 years. So as you've seen, of course, in this specific case, that's why I wanted to show you, is that law enforcement wasn't able to connect the dots. And because of this, unfortunately, she was in captivity for 18 years. But let's imagine what will happen if we had a different system, So, of course, we will try to really rewrite the history in this case. So the first step, of course, for this intelligent advisor system is to create a knowledge graph, as you can guess. And around the J.C. case, but not only. And we will use the information available at that time with a few more data sources that now are quite handy for police officers. Our starting point, as usual in this case, is the, let's say, the witness statements, as well as criminal history, including modus operandi, and all the reports from parole officers or police officers that knocked at the Garrido's home. All these data, as you can guess, are unstructured data. For these, as we will see in the example later, we can use definitely LLMs to extract relevant information that will be stored in the graph quite nicely. And then we have tons of other structured data like traffic cameras records, car registry, criminal records, etc. That can be easily transformed in pieces of this graph. Here we have a simplified schema where we can imagine, we can see that we have a person in the center connected with different events with different title, could be suspect, victim, or witness. We have details of previous offenses. And interestingly, on the bottom side, we have details about the car owned by these people with the details of the number plate that can be recognized by traffic cameras, for example. This is really all available. And on the top, we have the unstructured part with the details of the entities and the relationships extracted from the text. But let's see a portion of this graph. So in this case, in this part of the graph, we have, of course, the victim connected with some relatives, in this case, her stepfather, that was also a witness of this event. We have the details of the abduction event, where we explored the offense, the type of offense with all the details and the location that will be, let's say, useful to process later on. Here, what I would like you to see is the witness statement explosion, let's say, or the recognition that happened around the witness statement. Because, as I said, we can easily configure LLMs, even generic LLMs, to recognize, for example, human trait, vehicle details, ethnicity, comments from the let's say from witness statement. In this way, we can easily extract from text relevant information about the, let's say, about the event that we can process later. And this will simplify, of course, as you can guess, the detective effort to go through this enormous amount of data. On another side of the same knowledge graph, we have instead all the offenders' details. In this example, of course, we took just the details we had about Felipe Garrido, that, as I said, was a known sex offender. We have all the offenses. He was also arrested. That's why he was on parole. And interestingly, we have also the details of this gray sedan that he owns. Thanks to that, we can easily connect with all the, let's say, the times that this car has been seen around the abduction site. And even in this case, we have a lot of details related to, let's say, the parole officer reports or the police officer reports. You have to imagine that in the real, let's say, database, we will be plenty of this type of data, because unfortunately there are a lot of offenders in the database. That's why it's important to offer in this ideal, let's say, intelligent advisor system, a mechanism that will allow these detectives to operate, to access to this knowledge graph without sitting in front of the desk. So by using, of course, the language models and combining them in this nice agentic AI infrastructure, we can easily take questions and convert them in multiple queries against the graph to extract a relevant piece of information. So imagine for a second this scenario, that there is the detective speaking with JC, let's say, stepfather that witnessed the event, and he reported that there was this gray car that took JC. And suddenly he can ask immediately through this system, imagine like a Siri-like system, who are the registered sex offenders owning a gray car that passed through any ENPR camera in a radius of 5 miles from Salt Lake Tower, that is the location of the event, around June the 10th. So in this way, the system can convert the question in let's say, in a cipher queries and get the results. And ideally, he can show immediately to the witness a sequence of images of the potential offenders. So maybe that in this way, this case would have been solved in 18 hours, not in 18 years, actually. And of course, even by using these techniques to extract relevant data, we can be flooded by information from the graph. You know, imagine that also we are extracting a lot of insights from it. So this could be overwhelming for for detectives. That's why we tested another scenario in which once the data has been extracted and properly organized thanks to the graph, we can pass this information to generative AI tools that could summarize this data properly, and they can generate nice reports in which they are able to, let's say, perform matchmaking, even though they have to match a gray car with a gray sedan, for example. And it's working pretty well in helping the law enforcement officers. Of course, as I said, this was just a case. I would like to remember again that this same approach of the intelligent advisor system can be applied in many, many different domains where you have to extract relevant information from unstructured data combined with structured data, and then use, for example, LLMs to get proper access to a vast amount of knowledge that is both specific and generic. That's why the time to act is now, because we have seen a lot of powerful technologies, and knowledge graphs for sure are quite a mature technology. So that's my recipe, let's say, for starting immediately your journey in this sense. So the first step is clearly to identify inside the organization some mission critical decision processes, in particular in the areas where you can struggle with gathering data from a variety of data silos, for example. And then you can assess your current AI approach, in particular if you are struggling with the black box nature of this tool, or because you are suffering hallucinations, etc. Again, these two are good indications of where to start acting. At that point, you can create your vision, so what you would like to do, identify a small task and start with it. Because what I generally suggest in this case is to identify a task that is meaningful, but not that big, in the sense that it could be performed and implemented in a short amount of time. This will shorten the time to value and will motivate you to use it even more. And of course, the same approach should be used for building the knowledge graph in this way. So don't try, as many companies, to take all the data available and create an enormous knowledge graph. You should focus on the goal that you have, decide what are the data sources that could help you in this goal, and then start creating your first knowledge graph that you will iteratively create. And by the way, if you are interested in this topic, you can also check my book, where here you can find an easy QR code to get some discount, I guess. And with this promotion, asked by my editor, I would like to thank you for the opportunity to share these few ideas today, and I'd like to listen to your questions, or, since we are a bit late, to, let's say, speak later during this conference. And if you need, just don't hesitate to contact me. Thank you.